Hello everyone, my name is Siamak Ghorbani. I'm from the People's University of Russia. Uh, Today I'm going to present a paper entitled Static and Dynamic Mathematical Modeling of an USM rack. As you know, material and our process are divided to two groups, conventional and unconventional. Ultrasonic is the unconventional machining and manufacturing process. In this process, the material of workpiece is removed by the repetitive impact action of abrasive particles. The erosion takes place by the abrasive particles, which are carried by a liquid medium in the form of slurry. The shaped vibrating tool is used to produce the impact, as you can see from the figure. Ultrasonic machining has a lot of application for machining hard and brittle materials, for machining of die and tool of drill, to fabricate silicon nitride turbine plate, and it is used to cut diamond in desired shape, and so on. The main criteria for this process is material removal rate, geometrical accuracy, surface finish, tool life, consume power, and on this criteria affects the amplitude, frequency, abrasive grain size, and applied static load and material for tool work and slurry. And all of the subject of the ultrasonic machine is subject to the vibration, and this vibration is between 240 kilohertz, and the tool vibrates gives the amplitude of around 5 micrometers. And the magnification factor for the amplitude of vibration is dependent on the design of the ultrasonic rack, and damping characteristic of the system is a main parameter that affects the amplitude frequency of the system actually. So the purpose of our work is to develop a mathematical model which makes it possible to simulate the excitation of oscillation by a random force action on a rack models made of different materials to reduce vibration during USM using material with high damping capacity such as synthetic granite. So as you can see from the figure, the rack is box-like shape, and it is and on the height it consists of two sections. To calculate the deformation and vibration frequency of the rack, we represent the static and dynamic models in the form of an elastic freewheeling rod with a concentrated mass at the free end. And we use the theory of elasticity. So we use the equation 1 to calculate the curved axis of a cantilever beam with a constant rectangular section, and we apply this equation to a hollow section beam of the shape of a trapezoidal shape, and variable moment of inertia along its length. So I mean equation 2 and equation 3. And theoretical analysis of the frame oscillation is greatly simplified if we consider only the vibration modes corresponding to the first harmonics of the natural oscillation spectrum, since it is on this harmonic that the greatest oscillation amplitudes are observed. To solve the problem numerically, we mentally divide the stand along the vertical axis into a large number of sections, the dimensions of which are easily calculated from the data in figure 1. So we achieve the reduced mass of model under bending, and since we start from the condition that the natural oscillation frequency of the rack and the computational model are equal, so we can write for the amplitude values of the velocity the equation 5. We substitute the equation 5 to 4, and we get the equation 6, and at the end we get the frequency of the rack natural oscillation of variable cross section. As a result, we calculate this equation for our case, and we get the torsional bending vibration of the upper part of the bed in the frequency range of 2 0 to 2000. And as you can see, this slide compares the vibration amplitude of the rack for two different beds made of different materials. So as you can see, the bed made of synthetic granite has less vibration amplitude. It means that it has better damping capacity. So as a conclusion, you can say that the synthetic granite has decreased the vibration amplitude about 83% from 77 micrometer to 13 micrometer, and the development of this computer model allows the simulation of the excitation oscillation by a random force acting on rack models made of different materials. Thank you for listening.